Complex numbers, de Moivre's theorem. What are they? Complex numbers are a mixture of a real number and an imaginary number. Why? Alternating current, or AC electricity, changes between positive and negative in a sine wave. Interesting fact, black panthers are great swimmers and are one of the strongest tree-climbing big cats. Now, let's talk about de Moivre's theorem. Here we have a complex number, z is equal to r times the quantity of cosine theta plus I times sine theta. Let's multiply this complex number by the same complex number. Remember, when we multiply these types of complex numbers, we multiply the moduli, or r, and add the arguments, or theta. Let's simplify. So now we have z squared is equal to r squared times the quantity of cosine 2 theta plus I times sine 2 theta. Let's multiply this complex number by itself again. And remember, when we multiply these types of complex numbers, we multiply the moduli and add the arguments. Let's simplify. So now we have z cubed is equal to r cubed times the quantity of cosine 3 theta plus I times sine 3 theta. So this keeps going on forever and ever, so we can create a general formula. Do you have an idea what it is? It is z to the n is equal to r to the n times the quantity of cosine n theta plus I times sine n theta. Now, let's take a more detailed look on why this is the case. So once again, we have our complex number z is equal to r times the quantity of cosine theta plus I times sine theta. Now let's multiply it by itself. Right now we have z squared is equal to the sum of two numbers squared. So let's go ahead and expand that. And so now we have z squared is equal to r squared times the quantity of cosine times cosine plus I times cosine times sine plus I times cosine times sine plus I squared times sine. Now, let's rearrange the terms so I squared is on the left-hand side, and we're doing that because I squared is negative 1, and that means the i's are on the right-hand side. Now, let's simplify. Right now we have z squared is equal to r squared times the quantity of cosine times cosine minus sine times sine plus I times cosine times sine plus I times cosine times sine. Our next step is to factor out an I so that we can look like a fancy complex number in the form of a plus bi in the curly brackets, where cosine times cosine minus sine times sine is a, and cosine times sine plus cosine times sine is b. Now, let's simplify the a part and b part of our fancy complex number in the curly brackets. So cosine times cosine minus sine times sine becomes cosine squared minus sine squared, and cosine times sine plus cosine times sine becomes 2 times cosine times sine. Right now we have z squared is equal to r squared times the quantity of cosine squared minus sine squared plus I times the quantity of 2 times cosine times sine. So we have one more step before this equation looks like de Moivre's theorem general formula. Do you know what it is? We need to use the double angle formulas. That makes some sense if you think about it. We multiply the moduli and add the arguments. Since we're multiplying the same complex number, we have double the argument, so we have double the angle. Now, let's use the double angle formulas so we can substitute for a and b in our fancy complex number. So cosine squared minus sine squared becomes cosine 2 theta, and 2 times cosine times sine becomes sine 2 theta. So this detailed approach shows why de Moivre's theorem works. Now, let's see de Moivre's theorem in action. Before we do that, let's talk about the equations we might need. Here we have the standard form and the trigonometric form and how to convert between the two. We also might need the unit circle, depending on the angle or argument. Now, let's take a look at the example we're going to discuss in today's video. Let's read the steps. Step 1, draw. Step 2, use the formulas. Step 3, follow order of operations. Let's read the question. Use de Moivre's theorem to change the quantity of 4 plus 4i to the 5th power to the form a plus bi. On the top right, we have de Moivre's theorem. Z is equal to r to the n times the quantity of cosine n theta plus I times sine n theta. We also have r is equal to the square root of a squared plus b squared, and we have tangent theta is equal to b divided by a. Now let's get started with the question. Now we're going to draw a coordinate grid with the real and imaginary axis. A is equal to 4, so let's go 4 in the positive real direction. And B is also equal to 4, so let's go 4 in the positive imaginary direction. Now we know where 4a plus 4b is. We need to find the modulus and the argument. Now let's find the modulus, or the black line, using the Pythagorean theorem. A squared plus b squared is equal to c squared. Now let's substitute 4 for a and 4 for b. So now we have 4 squared plus 4 squared is equal to c squared. Let's simplify, and 4 squared is 16, so now we have 16 plus 16 is equal to c squared, and the sum of 16 plus 16 is 32. Now we have 32 is equal to c squared. Let's take the square root of both sides, so we have c is equal to the square root of 32. If we simplify the square root of 32, we can rewrite it as the square root of 16 times the square root of 2, and the square root of 16 is 4. So c, or the modulus of r, is equal to 4 times the square root of 2. Now we need to find the argument by using tangent theta is equal to b divided by a. Since we're running out of room, let's get rid of some of that work. And now we can substitute 4 for b and 4 for a. Make sure that you remember tangent is opposite over adjacent, but since the numbers are the same, it doesn't really matter in this case. Now we have tangent theta is equal to 4 over 4, and 4 divided by 4 is 1. So now we have tangent theta is equal to 1. Let's take the inverse tangent on both sides. So theta is equal to tangent inverse of 1. And tangent inverse of 1 is pi over 4. So now we know our argument. That is why having the unit circle is handy. Now we can use Moivre's theorem. So let's substitute 4 square root of 2 for r and pi over 4 for theta. So now we have z is equal to the quantity of 4 square root of 2 raised to the 5th power times the quantity of cosine of 5 times pi over 4 plus I times sine of 5 times pi over 4. Let's simplify a little bit. So the quantity of 4 square root of 2 raised to the 5th power is 4096 times square root of 2, and 5 times pi over 4 is 5 pi over 4. Now we can use that unit circle again. Cosine of 5 pi over 4 is negative square root of 2 over 2, and sine of 5 pi over 4 is negative square root of 2 over 2. Now let's distribute that 4096 times square root of 2 to each term inside the brackets. And now let's simplify what we have so far by multiplying 4096 times square root of 2 times negative square root of 2 over 2. And the result is negative 4096, and that is because square root of 2 times square root of 2 is 2, and 2 divided by 2 is 1, and we're still left with a negative. Now let's simplify the last part. Since we have the same numbers, we get the same result, so we have negative 4096i. So z is equal to negative 4096 minus 4096i. And that is example 1. Now it is your turn. So go ahead and pause the video here so you can take your time to answer this question, and I'll show you the result in 3, 2, and 1. Did you get it correct? Superb. If not, there's always tomorrow.